In this lesson, we will start to look at practical navigation techniques. No matter how sophisticated navigation systems have become, there is always a chance of gross navigational errors. Position awareness should become a natural instinct for pilots, and you should never relax and become complacent that modern navigation aids and wizardry will stop you from getting lost. Additionally, not all aircraft benefit from modern technology. The 1 in 60 rule is a rule of thumb that gives a quick and simple method of remaining on our intended flight path. In other words, the path we should follow over the ground. The intended path over the ground is referred to as our planned track. Imagine a line exactly 60 centimeters long. Now raise a perpendicular on one end of the line and make this 10 centimeters long. The angle annotated Z in the diagram on the screen will measure 10 degrees. If the perpendicular were changed to be 5 centimeters, then the angle would be 5 degrees. Likewise, if the line was actually 60 miles long and the perpendicular was 5 miles long, the angle would still be 5 degrees. This phenomenon of 1 degree for every 1 mile over 60 miles is known as the 1 in 60 rule and can be adapted to keeping an aircraft on the planned track. The geometry of it is quite simple. The rule of tangents explains why it works. The tangent of an angle is the relationship of the opposite side divided by the adjacent side. The table on screen illustrates some examples from 1 degree to 20 degrees. The actual tangents appear to be meaningless, until, that is, we multiply them by 60. For each angle, the tangent, when multiplied by 60, becomes very similar to the angle itself. For example, the tangent of 1 degree is 0.017, which becomes 1.02 when multiplied by 60. The angles up to around 20 degrees illustrate this, where the tangent for 20 degrees, when multiplied by 60, becomes 21.84. For practical purposes, the 1 in 60 rule is only used for examples of up to 20 degrees, as the error then becomes larger. Clearly, as we fly along, we are not concerned with the tangents or mathematics. We just want to develop a simple rule and formula to use in a practical manner. Suppose the line of 60 nautical miles were from one position, A, to another position, B, that we had planned to fly. In other words, our planned track. Also, let's suppose we take a fix of our position and find that we are 5 nautical miles left of our planned track. The triangle would look like the diagram, and we know that the angle we have flown away from our planned track is 5 degrees. In other words, we have deviated from our planned track by 5 degrees. Suppose our planned track had been 100. We can say that our actual track was 095 degrees. The actual track flown is sometimes referred to as track made good. So our track made good is 095 degrees. Of course, it would be very rare that our fix will take place at exactly 60 miles. So we need to understand how to adapt this rule to distances other than 60 miles. We will call the angle that we have deviated from track the track error. To calculate the track error, it is simply the distance off track divided by the distance gone along the track, and then multiplied by 60. For example, you find yourself 6 miles right of track after 40 miles along track. What is the track error? The formula is distance off, 6, divided by the distance gone, 40, times 60. Answer, 9 degrees. try to keep the maths simple. For example, it is easy to divide 60 by 40, as this is 1.5, and then multiply the 6 by 1.5. Also, it may be that we had travelled 38 or 39 miles along track, so round it to 40 to keep the maths simple. With practice, you can do all the calculations in your head. The idea is to rapidly come up with the track error. Having calculated the track error, we need to decide how to use it to continue our navigation. Clearly, we do not wish to continue deviating from our planned track. Let's put some values into the example. Suppose our planned track is 090, and the total distance is 100 nautical miles. We have deviated by 9 degrees, so our track made good is therefore 099. We need to turn to the left to stop the deviation from track. If we were to turn 9 degrees left, then we would fly a track that is parallel to our planned track. We would continue to remain 6 miles displaced to the right. So how many degrees should we turn through? Something more than 9 degrees. Additionally, do we want to get back onto the planned track, or make a heading for the turning point at the end of the leg, some 60 miles away? Consider another triangle as shown on the screen. It is the same size and shape as the triangle depicting the track error. It can be seen that we would need to turn left by 9 degrees to parallel our planned track, plus a further 9 degrees to intercept our planned track. So we would turn left by 18 degrees and regain our planned track in the same amount of time that we have already flown up until the fix. For example, suppose we left at 1000 and took the fix at 1020. In another 20 minutes, we would be back on track at 1040. Once back on track, we would need to allow for the fact that we had deviated by 9 degrees, and this would have to be incorporated when planning a new heading. In this example, we would be back on our planned track, with 20 miles remaining to the turn point. This method of regaining track is known as the double track error angle method. The 1 in 60 rule can be adapted to give approximate solutions to many navigation problems. We have seen a quick and simple method of how to regain the planned track. Remember that track error equals distance off divided by distance gone times 60. If we apply double the track error, we will regain our track in the same timescale as it has taken up to our fix. Keep the maths as simple as possible, rounding up or down as required. It is a rule of thumb, not a precision calculation.